Okay, so the talk this morning is by Denis Benois, who will speak on p-adic Hodge theory.
Thank you. So I will just to finish to some remainder about basic properties of crystalline and Durham period rings. So I recall that we constructed two rings. Actually, B Durham is a field which is equipped with a continuous Galois action and filtration. And Becquerel is equipped also by induced Galois action. Frobenius operator. And we can also define, using just the filtration on B Durham, the filtration on Becquerel. Okay, so here are some basic properties of these rings. So maybe I already talked about some of them, but I will give a complete list now. So consider the graduation of this filtration on B Durham. So the factors are isomorphic as Galois modulus to Ci. Sorry? No, you can take tensor K, but that's fine without K. No, we don't need to fix K. So you can define a filtration also on decrease tensor K, but this is also fine. This? Yes, sure. Okay. The Galois invariants of B Durham are K, and the Galois invariants of Becquerel are K0, where K0 is, as before, the maximal unramified subextension of K. So this is totally ramified. So the third, the third point is a fundamental exact sequence. So maybe it would be better to talk about fundamental exact sequences, because there are some several ways to write more or less and code more or less the same information. So we start with Fontaine-Messing exact sequence. Let's recall that these two rings contain the element T, which is the logarithm of a Teichmüller lift of epsilon. Epsilon is the system of Pn fruits of a unity, and that the Galois group acts on T as a cyclotomic character, and Frobenius operator multiplies T by P. And we have a following exact sequence for any I big or equal to 0. Starts with QPTI. We go to fill I of B Chris plus. So recall that B Chris plus was a sum, so constructed before B Chris. This is a subring of B Chris, and B Chris was constructed from B Chris plus inverting T. And here we go to B Chris plus itself. And the map is given by the following operator. So the point is that this sequence is exact. Here, maybe the only immediate thing is that this term lives in a kernel of this map just because we know the action of phi on T. So we immediately see that this lies in the kernel of this map. Sorry? Yeah, this is again the filtration induced from Bidoram. Yeah. So the subjectivity and the exactness in the middle term are not obvious, and anyway, this is some delicate proof. There exists also an integral version of this exact sequence where B Chris plus is replaced by A Chris plus. And this is, so we can exactly determine the kernel in this case, but it is some fine computation in these rings. So for our goals, this is this suffices. And from this exact sequence, it's easy to prove the exactness of the following sequence. The first term is the same. Here we have the I filtration over B Chris, but not B Chris plus. This is not the same thing. And here we have fill 0 B Chris, and the map is the same. Some warning. Fill 0 B Chris is not B Chris plus. Sorry? Here I think it's again, so any positive. This is just a Frobenius minus 1, yeah. And the last exact sequence, which can be deduced, again, it can be deduced from the sequence B, which is maybe the most important view, its connection with the curve of Farc-Fontaine. Where this map is just a projection map. So induced by the injection of Bicris in Bideram. And in Fontaine-Farc theory, usually this ring is denoted by BE because of its importance. Before spatial notation hadn't existed, but now it exists. Okay. So, in particular, the exact sequence C says us that field 0 Bicris fixed by phi is QP. So you can take, for example, you take some, this canonical generator of kernel of a theta, and it lives in Bicris plus, and you divide it by t, and this is 1 divided by 1 by p minus 1, and it lives in 1 by t Bicris plus. But in fact, it lives in field 0 of this quotient. But it doesn't live in Bicris plus. Sorry, yes, but it doesn't live in so it lives in field 0 of 1IT Bicris plus, but not in Bicris plus. Sorry? Yes, yes. We can take here, sorry, we can take here. So, yes. But the idea is the same, so we get denominators, but which are not in the kernel of theta. Just to finish this list of rings of p-adic periods, I will introduce the last ring, the semi-stable, the ring of semi-stable periods. BST, which is defined by the following way. Let denote by x the logarithm of the following element, where as before, p script is this element of p and fruits of p in OC tilde. And the logarithm is always considered as a power series, so defined as by the usual formula. And we see that this term tautologically lives in a kernel of theta, or theta extended to the inverse p, so in the kernel of theta qp. So this converges in a discrete valuation topology in Biederam plus. And it can be proved. So this is some, sorry? Thank you. Yeah, so. The point is that x is a transcendental over the field of fractions of decrease. And the ring of semi-stable periods is defined formally by adding x to decrease. And we keep this ring with Frobenius. So Frobenius is already defined non-decrease, but it is not defined on Biederam. But view this definition in terms of logarithm. It is natural to define phi of x equal to px. And we keep decrease with a monodromy operator n, which is a derivation with respect to x. Sometimes for, to make some canonical choice, sometimes one multiplies this operator by some constant, but it is not so important in this talk. So from the definition, it follows that the monodromy and the Frobenius are related by this relation, and view the adic Grothendieck monodromy theorem, where the similar relation already appeared in the adic setting. One can see that this ring is a good approach toward the p-adic version of Grothendieck monodromy theorem. So now I would like to talk before start to overview the general formalism of Fontaine's theory, to give some particular case of this theory where many constructions can be seen explicitly. So this is a case of formal groups, and also the connection of this theory with the subject of Udi's lectures will be maybe more clear. The next paragraph, periods of formal groups. So let me start with the following analogy. So we start with a complex situation. Consider first some k, for example, some number field k. And we consider an abelian variety of a k. And we will consider the complex structure in X. So we consider the usual de Rham cohomology of X, or K. So this is a K vector space of dimension, so if X is of dimension D, so H1 de Rham is of dimension 2D. And inside we can consider what we will denote by fill, so the first term of Hodge filtration. Which is the submodule of holomorphic differential forms on X. And we can also just note, sorry? Yes. So that they are invariant forms. So we have a two-step filtration, canonical filtration on H1 de Rham. So this is field 0. And in this situation, maybe also we can describe the de Rham cohomology of X as follows. This is a quotient of meromorphic differential forms of second kind. And this means that they have no logarithmic poles. Quotient by exact forms. And in this situation, we have a periodic period map. Between H1 de Rham and the homology with values in C. So the period map, which is non-degenerate. So we consider X as a complex variety. Yeah. So yes, maybe it is useful to remark that we consider all over K, over F, yeah. It's not so much important, but it's more nice to see these objects over K rather than over C. But so we want to find a p-adic analog of this pairing. In the context of formal groups. So now let K be a finite extension of QP. And just for simplicity, really by simplicity, we will assume that K is unramified. And we will consider a formal group law, F, which is given by a power series in two variables. With coefficients in OK. Of finite height. Say H. And again, for simplicity, only for simplicity, I will assume that F is one-dimensional. So one-dimensional formal group. So I just recall some definition which already appeared in Udi's lectures. So we will consider differentials on F, which are power series. So differential forms of this type, where F is a power series with coefficients in K. And we will say that omega is invariant. If and only if it satisfies so the natural property that omega of fx plus xy is equal to omega x. So if we consider f as the addition law, we can write this property in this form. So this is really the condition of invariance of a form.
Consider y as scalar.
Sorry?
That's if you consider y as scalar. Consider y as a variable.
Yes, but okay. So we have a following proposition. So let omega 0 be dx divided by, so we take the derivative, formal derivative of f with respect to y and evaluated it at y equal to 0. Just from the fact that when we derivate with respect to y, the series starts with 1, so it is invertible. So automatically this is a differential form with integral coefficients. So then a form is invariant if and only if it is a multiple of omega 0. So omega 0 generates the module of one-dimensional module of invariant differential forms. So the proof is very easy because from definition, just from the definition, if you write it down, it follows already that if a form omega is invariant, then it should be of this form. And one should only check that omega 0 is invariant, so it follows from the associativity of a group law. So just formal associativity of group. Sorry? Star, this is a definition of that, yeah. So this thing is, so f of x, x, y, and next you take the derivation, so f prime x, x, y, dx. And from associativity of formal addition, it follows that omega 0 is invariant. Now, let's denote by lambda omega 0 its formal primitive. So if omega 0 is of this form, so the formal primitive is this power series, which doesn't lie in OKX, but it has coefficients in K, in the field of fractions of OK. But the denominators are controlled, and you see that, so it lives in the divided powers, yeah, with respect to the ideal generated by X, so it has some sense crystalline nature. Definition. This primitive will be called logarithm of f. And from the invariancy of a differential form, we see immediately that the logarithm satisfies the following property. So it transforms the formal group structure to the additive structure. So. So, example, if we consider the multiplicative formal group law, then omega 0, so we divide dx by the derivative of this power, power series with respect to y, and evaluate it at y equal to 1, so we get 1 plus x, and lambda omega 0 is the logarithm of 1 plus x. So now let omega be any differential form, not necessarily invariant. Definition. It is not a finite height. Yeah. Okay. Definition. So we want to define the analog of differential forms of a second kind on abelian variety. And the definition is the following. Omega is a differential form of a second kind, if and only if its logarithm, so again the logarithm is defined to be the primitive of omega, if and only if lambda omega of fxy minus lambda omega of x minus lambda omega of y lives in the maximal ideal belongs. Thank you. So omega is of a second kind if it satisfies this property, the property of logarithms, but only modulo p. So the analogy of between this property and the complex situation probably can be explained by the observation that if we have a differential form of a second kind on an abelian variety, so we take its lift to CD, so we consider it as a function on CD. Then if we form this object, we take the primitive and take the same object, it is a periodical function. So another explication is that in crystalline theory, crystalline theory should control the behavior of object mod P. So we consider the logarithm property, but mod P. The second kind, it means that so it has no logarithmic zero. So for an elliptic curve, it shouldn't have residues. So this is a form of second kind, form without residues. No. Yeah. But exact is the differential of a meromorphic function. Yeah. And now we define the notion of an exact form in this setting. So we say that omega is exact if its logarithm is some trivial mod P. Yeah, so lies in P, OK, X. Now we consider the following object, which for us will be a generalization of the RAM cohomology in the context of formal groups. We take the quotient of forms of a second kind by exact forms. And I don't talk in this course about the theory, integral theory, so I don't take care of integral structures and take the tensor product. So with K. What? The same, yeah, so, yeah. And inside this, we define field 1 as the submodule, subvector space generated by the invariant differential form. X is F. Okay. What are properties of this object? So this is a dimension space, the finite dimensional K vector space of dimension equal to the 8. Next, from this definition, it can be seen immediately that that H1 DRAM, F, depends only on the reduction of F mod P. This is just some easy computation with power series. The further remark is that we can define first the Frobenius operator on the ring of power series. So sending X to XP, and phi will act as the usual Frobenius, absolute Frobenius on OK. And this operator extends to H1 DRAM. So H1 DRAM is a phi module. Yeah?
Omega 0, does it depend only on F1B?
No.
So when you say that H1 DRAM depends only
So when yes, this is a good remark. So H1 DRAM as just a k-vector space without a filtered structure. Yeah. And sorry. Where is the canonicalism? The reduction, yeah.
So you're not saying it's
Yeah. Yes.
You're not saying more than the dimensions are the same. What you're saying is a canonical isotope.
Yeah. Yeah.
But showing that all these rules, the remark is very good. It says canonical up good. The thing is more.
Yeah. Yeah.
It depends only.
Yes. Yes. Sure. Yeah. Yeah. So next, one can describe the structure of this phi module. So as phi module, yeah. This is a H1 DRAM is a k-vector space, okay, of finite dimension, which is H.
No, but it's fine, but you said that it can be expanded, like, what has
It means that, so you consider the action of phi under the forms of a second kind, and you should check that because you take the quotient here, you should check that it is well defined.
what's the relation H1 around and OK double one
H1F is a quotient of the forms of a second kind which live in OKX.
So what you actually mean is that on the form of second kind can be go to the whole.
Yeah. So as a phi module, F, so H1 DRAM F is generated by omega 0 with the relation of a form 1 minus alpha 1 phi plus alpha 2 phi square. So 1 alpha h phi h divided by pi of omega 0 is equal to 0, where alpha 1, alpha 2, alpha h minus 1 are 0 mod p, and alpha h is invertible. Okay, so now, yeah, I have a 10-minute, okay. So I will first state the theorem, and next, if I have time, I will give comments. So this is a theorem which was explicitly stated by Kolmeza, but this is in some sense a reformulation of the theory of Fontaine on p-divisible groups in these explicit terms. So we keep all notation and denote by TPF the Tate module of the formal group F. And let VPF be the corresponding p-adic representation okay, let omega be of a second kind. And let V be an element of a Tate module of F, which we write in the form V0, V1, and so on. Where, with respect to the formal group rho, PVN is Vn minus 1. So then, let's consider the following object, which we call integral or period of omega, which is a limit when n goes to plus infinity of Pn lambda omega of Vn hat, where Vn hat are elements in the ring A-inf, such that there are lifts of Vn under the theta map. So the statement is that this limit exists, so is well defined in B-Doram, in B-crease, and doesn't depend on the choice of the lift Vn hat. So we have some element in B-Cris plus. Second statement, it induces a non-degenerate pairing between the Daram cohomology of F and so by linearity we can pass to VPF. With values in B-Cris plus, which is compatible with the action of a Frobenius and the Galois group. So this means that if we take the class of omega, and the element V in VP, if we act on this class by the Frobenius, so this is phi of the period of the class. And similarly, if we act on V by the Galois group, so the pairing, this multiplies the period, so this makes G appear on the, act on the period. So in this statement, all points are easy to check, except the non-degeneracy of a pairing. And to prove this, so normally one should use pass to the dual object. And so by general formalism, the periods of dual objects are given by the dual by the inverse matrices. So the product of these two matrices, so the product of a matrix of a periods of F and the matrix of periods of a dual object is a matrix of a Tate motif. So which is invertible. So this gives the non-degeneracy of a pairing. But the dual object doesn't exist in the category of formal groups. It exists in the category of p-divisible groups. So we should a little bit extend the theory to check it. So I don't explain this in detail. But maybe I will explain the analogy with a complex integration and this definition. Yeah. Again? G. You take an automorphism, yeah, which acts on the Tate module. Yeah, and this is compatible with the action on the period ring. It says that the periods of a formal group over an unramified ring are crystalline. Yeah. but semistable is not crystalline. A formal group, for varieties, it covers only some small piece. Yeah. You should have good reduction to define a formal group. Yeah. So if K is ramified, so the periods doesn't live in decrease, but decrease tensor the field of definition of a formal group. Yeah. Yes, everything works, yeah. Yeah. Yes, one can write an integral version of this, taking the canonical lattice in H1 de Rham, because H1 de Rham, this is in fact a module of Dieudonné-Manin of a spatial fiber, but equipped with the filtration structure. And it has an integral structure, which is also covered from with almost logarithms. And we can write everything on the integral level. Yeah, and so no. Yeah. So maybe I will just comment this this definition of a p-adic pairing. So if we test it on the example of a multiplicative group, so over C, what we do, we have a complex period pairing. Here we have a canonical generator of H1 de Rham. Here we have we can take as a path the unit circle, say S, and you take the integral of a differential form, and this gives us 2pi. But we can write this same thing differently. So we cut this circle on n pieces. And here we have a nth root of unity. So we can write this also like n times the integral from 0 to zeta n dz by z. They are tautologically equal to 2pi, but we can also write that this is the limit when n goes to infinity of this sequence. If we do exactly the same thing over QP or CP, over C, if we take the integral from 0 to zeta Pn of a logarithm, of dz by z, this is a logarithm of zeta Pn, which is 0. So we cannot do it directly in C. But if it can, we take a lift of zeta Pn in A inf, we can take, for example, epsilon 1 by Pn. So we get so if you multiply by Pn, get Pn, the logarithm of epsilon 1 by Pn, which gives the logarithm of epsilon, which is t. And this shows that t is a good analog of 2pi in the periodic log. Just to finish, I have no time to deduce all easy but important corollaries from this theorem. But for example, if we pass to graded rings, so we take the graduation here and we take the graduation here, we cut this period on two pieces, the periods with value in C and the periods with values in C twisted by 1. And this gives the Hodge state decomposition for VP, in particular it shows that VP is Hodge state. I stop here. You mean the action of Frobenius on a power series? If you change it mod p, nothing changes.
Let's find the speaker again.